So welcome back. This is the third little tape. This is the last bit, fourth. And so this is a kind of weird situation. Again, we're just trying to do a different way of using the sum of the forces equals 0 or the sum of the forces equals ma. And on this one, I want you to imagine that you went fishing and you caught a fish. And you're so proud of it that you got it on the little scale thing saying how many newtons it is. And then you get in an elevator. And you notice when you get in the elevator, the mass tends to, the weight, the apparent weight changes. When you press the up button, suddenly it seems like it weighs more. And then when you're coasting past all the floors, it goes back to what the original weight was. And then when you get near your floor and the elevator slows, suddenly it appears like it weighs less. And so you start saying, well, what is the weight of this fish? It keeps changing. And the reason why the apparent weight keeps changing is because sometimes you have an acceleration acting on the fish, and sometimes you don't have an acceleration acting on the fish. And if you try and solve this by thinking about it, I think, especially when you first begin, it can be quite confusing. But if you recognize this is just Newton's second law. Let's draw a diagram and apply it. It just falls out. So that's the game we're playing. We have a Newton meter, a little weighing device. I'm sorry, let's get that. I always forget my pen. We have a little Newton meter, a weighing device. We have some kind of string, and here's our fish. The thing to realize is that the fish pulls down on the little cord, which causes a tension, and the tension pulls down on the weighing device, and the weighing device reads the tension. It doesn't really read the fish. It has no idea the fish is there. You can fool it by pulling on it, and it doesn't know that you've not got a fish. So if you had one of these smart weighing devices, you could pull on it, and it would say, "Oh my word, Tony, you caught this really enormous fish today." And I'm going to say, "Watch this. I just caught another one." And it would be really confused because it has no idea. All it knows is what you pull the string with. Yeah. It reads the tension. Okay, so we're going to have it in a non-accelerating frame and see how it behaves. And then we'll have it in an accelerating frame and see how it behaves. 4 kilogram object hangs while, we're going to have it on we're going to just have it to go straight to the acceleration. 4 kilogram object hangs on a force gauge while traveling in an elevator that is moving upwards and speeding up. Its acceleration is 3 meters per second squared. What is the apparent weight? The weight is the weight. The weight is mg. The tension now is the thing. We've got to get the direction of the acceleration. Hangs from a force gauge while traveling in an elevator that is moving upwards. So my velocity is upwards and speeding up. What must my direction of acceleration be? Upwards, because when they're both pointing in the same direction, they're speeding up. Okay. I want to find what is the apparent weight. T is ap weight. That's the first thing. You've got to know that tension is the apparent weight. The sum of the forces vertically is equal to ma. That's the guy I'm looking at. Let's change coloured pen so you can see that a bit easier. I'm going to look here. And that is 4 kilograms. So I say positive, negative. I say plus t added to minus 4 times 10 because that's just my that's just my gravitational field strength, is equal to my mass, which is 4, times my acceleration. And my acceleration is 3 meters per second squared, and it's pointing upwards. So T minus 40 is equal to 12. So T is equal to 12 plus 40, which equals to 52 newtons. How did I get
3?
The 3? Oh, because there. Yeah. It's got a bigger apparent weight. And that's what happens when you're in an elevator and you're accelerating up. It's that first initial, and if you've ever been on a big high-rise elevator, you feel it in your knees. I went up the World Trade Center back, back in '79. I went up the World Trade Center. It was originally about a quarter of a mile high. That's how big the World Trade Center is. And it had, I think, an express elevator that went to the observation platform. And you got in that, and when they pressed the button, you felt your knees kind of like buckle a little bit. And that's the acceleration. So notice all the signs, okay? Let's go to the, and you could have done this by saying, well, the weight is 40 newtons, and then MA is 12, but I tell you, half the people would take the 12 away from the 40, and the other half the people would add the 12 to the 40. And it's like snatches of sentences. This is writing in sentences. Let's do another one. A 4 kilogram object hangs from a force gauge. While traveling in an elevator, moving upwards and slowing down. Apparent weight equals T. Find T using, if you like, the sum of the forces on the 4 equals the mass of the 4 times the acceleration of the 4. To be very specific, I go plus T added to minus 40. This is positive and this is negative. Is equal to 4 times, now my acceleration is negative direction. And I got that from the wording, slowing down, moving upwards and slowing down. So then I go, oh, that's not going to be 3 meters, that's going to be minus 3 meters per second. So T is equal to minus 12 added to plus 40. So T is equal to 28 newtons. So all I did there was I reversed the acceleration. Now I'm at the top, I'm near my floor, and this thing's slowing down and my fish seems to weigh less. And in an elevator, if you feel that, you kind of feel that lightness. You feel lighter for that instant while you're slowing down. That's where it comes from. And my plea to you in this is, just let the math take care of it. Draw a diagram. And then just let the math take care of itself. It's the physics here is in the diagram, knowing that that acceleration is pointing downwards because of what the words say. And it falls out. It's a trivial problem because it falls out once you have a decent diagram. Without a decent diagram, man, it's like, well, what happens here? And you can turn yourself in knots with it. So watch out for that. It's a very easy point, and it's a shame not to get it.